Hello everyone, my name is Aditya Shokradesha and these are my teammates Shataki Bonik and Shrutapad Tithi. Today we'll be talking about our project utilizing convolutional neural networks in classifying cassava leaf diseases. So the motivation is that the 80% of household farms in sub-Saharan Africa cultivate cassava and yet they suffer from viral diseases which significantly reduce yields. So the current disease detection methods are like farmers have to go towards the government-funded agricultural experts and which is a very expensive and labor-intensive process, and it consumes a lot of time as well. So the possible solution is that we can leverage the deep convolutional neural networks so that the common leaf diseases can be detected early, and it can also be used to effectively boost and treat the crop productivity. So the dataset we've used was the cassava leaf disease classification dataset from Kaggle, and it consists of crowdsourced images captured under diverse field conditions such as variations in lighting, camera angles, background clutter, potential annotation, noise, etc. So the data is like dataset contains 21,397 cassava leaf images, and they've been classified into 5 classes: CVB, CBSD, CGM, CMD, and healthy. All the full forms are given over here. So the input is that the Kaggle dataset has the images in JPG format. The original image resolution was 800 by 600 pixels, and these have been resized for model input to 224 by 224 pixels for the baseline model, and for the upgraded model, it was 299 by 299 pixels. So the output is just the 5 classes of the cassava leaf images. So and we also did like a train test validation split. The training data was kept to be 70%, the validation was 15%, and the test was 15%. So we can see that there's a class imbalance problem from the pictorial representation over here, with the most frequent class being the CMD and the least frequent class being the CVB, and there's imbalance ratio of 12.1:1, which has been mitigated by different data augmentation techniques that we have used. So for the baseline model, we chose to use ResNet 50, which is developed by Microsoft Research. So it basically contains residual connections, the skip connections to solve the vanishing gradient problem. It has architectural depth of 50 layers. So basically, this model has been pre-trained on ImageNet, and so it is already robust and contains generalizable features that can be transferred easily. And with the 50 layers, ResNet 50 strikes an optimal balance between being deep enough to capture complex disease patterns, but not being so large so that it requires computationally expensive resources. So the data augmentation process is that we did some randomized resize crops, some horizontal flip, rotate, random brightness, contrast. We also normalized that. An example of an original image is this one, and the augmented images of this one. The evaluation metrics are precision, F1 score, recall, support, and accuracy. All these are state-of-the-art evaluation metrics for identifying the performance of models for classification tasks. So the ResNet 50 performance is like the training and validation accuracy was close to 70%. As we can see from the normalized confusion metrics, the model ResNet 50 does really well on one of the classes, but performs poorly on the other classes. So we'll look into how the advanced model mitigates that. So the class-wise performance for this ResNet 50 was that the CVB CPSD had moderate precision, was the CGM had high precision, the CMD was the best performing class. Our model did very well on this one, and the healthy class performed moderately well. As for the RC curve, this is the random, the dotted line signifies the random performance, but our model did relatively well, but not like in the ideal situation where the curves would go straight up and then flatten out as soon as possible. So we'll look into this. So for the upgrading the baseline model, we use the efficient B0, which has optimized efficiency because like it uses compound scaling, which improves accuracy, speed, and model size without excessive computational cost. Since we use the B0 version, so it offers a balance between the performance and efficiency, being the smallest version. It also outperforms larger models like ResNet 50 in terms of accuracy per parameter. It has also been pre-trained on ImageNet, enabling strong feature extraction. It boosts performance. It has been trained on fewer parameters, so it reduces overfitting, and is ideal for imbalanced data sets. And it is also computationally efficient as it requires less memory. So comparison between ResNet and EfficientNet B0 is that the architecture backbone is the same for both the cases. The input sizes vary, as you can see over here. The data augmentation was kept to be same because we wanted to compare on similar grounds. The training set was set to be 1600 samples for the ResNet 50 because we ran it locally. But for the EfficientNet B0, we used the full set because we were able to run it on a server. So the epochs was 8 epochs and 10. So, but we kept the batch size to be same. As for the loss function, we use the cross entropy loss for the baseline model and the level smoothing loss for the efficient B0. We use the level smoothing loss because like it makes sure that the network is not over confident and is better calibrated. As for the optimizer and Euler schedule, we use the Atom optimizer with a learning rate of 0.001 for the baseline model, but we use Atom W with a learning rate of 0.0005 with the weight decay of 1 e to the power minus 4 because like the Atom W applies weight decay directly to the parameter update, leading to more consistent regularization and generalization. And we also use the cosine annealing Euler scheduler because like it starts off with a really high learning rate and rapidly goes down and then further rapidly goes up, sort of like mimicking like a warm restart instead of a cold restart. So we can see the model performance over here. The efficient net B0 classifies all the classes fairly well compared to that of the ResNet 50 over here. And as for the ROC curves, for the efficient net B0, it performs sort of like an ideally because it goes straight up compared to those over here. And also like the AUC values over here are far greater than that presented in ResNet 50. So the training accuracy came to be 91.45, whereas the validation accuracy came to be 84.5 for the efficient net B0. And also these had like a precision recall and F1 score of 84%, which are far greater than the ResNet 50 model. So the final key takeaways is that the efficient net B0 offers a balance between accuracy and efficiency. It's already pre-trained on ImageNet and it trains on fewer parameters, but we can further improve it by enhancing performance by doing the hyperparameter tuning, doing advanced data augmentation. We can also address class imbalance by using further techniques like SMART or advanced post-processing methods. So our group had prior experience in working with image classification problems using VG16 nested one-to-one models. These are the references that we've used. Thank you.